In this presentation, we will cover the methods for preparing data for analysis and visualization. The intent is to cleanse the data so that there is the highest quality data available for analysis. The first step to preparing data is to undergo a data exploration phase. The purpose of the data exploration is to identify if there are any strange things going on with your data. The data exploration can include several different types of analyses. One type is data summarization. This includes an analysis of various columns of data regarding the minimum and maximum limits of the data, how often each unique value occurs. It can include descriptive statistics such as the mean, median, standard deviation, and so on. The purpose of summarizing the data is to identify if there are any outliers, identify if the mean makes inherent sense, and to really check at face value whether the data makes sense. The second type of exploratory data analysis is to examine the distribution of the data. This is often done by creating histograms, which is a graphical way to see how the data is spread out. The histogram will allow you to identify outliers as well as determine how frequent values occur. This will also allow you to assess the type of distribution to determine if the data is skewed or not. The third type of exploration is to look for correlations. This is used to determine if there are any underlying relationships between numeric columns of data. The reason this may be helpful is to further inform you about possible relationships between data elements that may lead to further investigation and inquiry. So why is exploring data so important to data preparation? First, we may find something that doesn't make sense in the data. The data exploration may help to find outliers, blank values, and trends in the data that just don't make sense. Second, we may discover something interesting and new that is relevant to the client. And last, you can provide a deliverable to clients in the early phases of the analytics project. Let's take a look at some examples of data exploration using frequency plots and histograms. The purpose of these plots are to find strange patterns in the data that should be explored further and explained. For example, let's say we had lab data and we assessed the histograms of the lab data over a period of a week and found that there were a high frequency of certain values that just didn't make sense. We may need to look into this further, and after further investigation, we may find that these unlikely values were a result of a faulty pipetting machine in the lab. Next, let's say you have patient data, and you find that you calculate the frequency that unique patients occur. In doing so, you see that there are certain patients that have the same first name, last name, social security number, and other identifying information, but the only difference is the address. This may have occurred because the patient moved, but as a result, the patient is now identified as two unique patients, and this shouldn't be so. Therefore, you make the decision to remove the duplicate entries and update the patient's address with the most recent encounter. These are all examples of how data exploration can inform an analyst on changes that need to be made to data before the data can be used for analysis. Many times through data exploration, you will find that there are some quality concerns with the data. You may choose to use the data without making any alterations. Obviously, this option is not favored because it may lead to misleading conclusions. Second, you may choose to modify or delete data before progressing with the analysis. This is a solution that will improve the quality of the data for analysis, but this is truly a temporary solution. The third option is to notify the IT department of quality problems so a permanent solution can be explored. As you'll see throughout this lecture, data prep is often a result of data being captured in a less than optimal way. Therefore, if you can create a better method for capturing and storing the data, this may help to minimize the need for data prep. Regardless of the option you choose, it's important to keep track of any problems you encounter and mark down the date and time of when the problem occurred and when you discovered the issue. You may ask why this is important. It's important for a couple of reasons. First, It shows that you did your due diligence and realized the quality issues. It also may show that you're taking the necessary steps to remedy the situation. Finally, it can help in future analyses so you can predict the data prep that will be required. We're going to dig into the second option a bit further. As a data analyst, you are often given messy data, and you are forced to modify and delete data in order to improve the quality. Missing data is incredibly common. The challenge is that missing data isn't often identified by a blank field. More likely, there will be a filler value in place of a blank entry. If the data is textual, the text NA or null may appear in place of a blank entry. If in numeric fields, there may be a filler value such as 9999 or negative 9999. In a date field, a blank entry may just default to 11-1900. There are many examples of how blank entries can be substituted with filler data. Consider the impact that this can have on your analysis. If you're working with a numeric column of data, and the data ranges from 0 to 500, and any blank entry includes the value of negative 9999, if we were to take the average of the field with the filler values included in the analysis, this would skew our average to a lower value. So, what should we do with missing data? If I were to ask you what data is missing in the spreadsheet above, how would you answer that? Take a moment to look over the data and try to answer this question on your own. You probably saw that there are filler values entered in two of the columns. You'll note that for patient ID AC456, a default date was entered. This is missing data. Also, for patient ID AE012, a default value was entered for weight. This begs the question, how will you handle this missing data? What would you do with those filler values? The solution may seem too simple. Just remove the filler values. That way, you have cleaner data and no confusion regarding what is truly there and what is a filler. There are numerous options for handling missing data. The most common and straightforward method is to remove the data. Be careful with this step though. Sometimes it's not enough to just remove the value, the filler value for a missing field. Sometimes it is enough to just remove it. It really depends on the intent of the analyses. With some situations, if a missing value occurs for a patient, it may be best to remove that patient entirely from the analysis. The best advice is to be consistent. Another way, besides removing missing data or fillers, is to use imputation. Imputation is a method of substituting the missing data with an actual value. This can be a bit tricky to undertake because you're making some huge assumptions. Let's look further at this. Let's say that a value is blank. You may choose to fill that blank value in with a 0. This really should only be used in situations where a 0 value was entered into the data as a blank rather than including a value. Also, this should only really be considered for numeric data. Consider for a moment inpatient stays, and if the patient stayed for less than 1 day, a 0 value would make sense. This may have been entered into the database as a blank entry instead of a 0. Therefore, replace the blank with a 0 would be appropriate. However, if you replace a 0 value in a column such as with heart rate, a 0 value would skew the data incredibly. A blank was likely entered because heart rate was not captured for that patient. Another imputation method for categorical data is to replace missing data with a word. This word may be something like missing or not available. The reason for this is so you can determine how often missing fields occur. Another method for quantitative data is to replace missing values with the mean, median, or mode value. The great assumption here is that a typical patient might have a value close to the mean. So by filling in blanks with the mean, it will be a close enough value. This can be misleading and dangerous because you are assuming that what is typical will occur for all blank entries, which just might not be the case. Lastly, you can add a constant value to missing fields. For instance, you may want to add the numeric entry of -9999 as an indicator that a field is missing. This is fine to do, but eventually these fillers will need to be dealt with when you analyze the data. A final approach to dealing with missing data is to get the value from elsewhere. For instance, if you have the patient's date of birth missing from a spreadsheet, maybe you can fill in that missing field by finding the patient's date of birth in a different location of the database. Another common quality concern is with data that has the presence of outliers. Outliers are defined as values that are quite different from most other observations. Unfortunately, identifying outliers is a very subjective process. Consider this for a moment. Let's say you have a column of data that includes ages of patients. You see that there is a patient that has an age of 1,200 years old. Do you think that this is an outlier? Probably. No one has ever lived to be this old. But what if a patient was 110 years old? Is that an outlier? Well, maybe it is real data, but it may still be considered an outlier. Essentially, an outlier is any value that just isn't typical to see and can skew the analysis at hand. What if you were dealing with monetary data, such as determining the cost of inpatient stays? Would you consider a single inpatient stay costing $1.2 million to be an outlier? This really depends on your data. Maybe it is typical if you are looking at high-cost patients. Maybe this is rare if you aren't. It's up to you as the analyst to determine if something is an outlier and then take the most appropriate course of action. There are quantitative methods for identifying outliers, but these methods are really intended to guide you into finding outliers rather than taking the subjectivity entirely out of the process. One way with numeric data that is normally distributed is to use the method IQR times 1.5. Essentially, you take the value at the third quartile and subtract out the value at the first quartile to get the interquartile range. Then you multiply that value by 1.5. Whatever that value may be, you add it to the third quartile. Anything higher than this value is considered a possible outlier. You may also take the IQR times 1.5 and subtract it from the first quartile. Anything less than this is a possible outlier. Another method is to look at the distance of a value from nearby neighbors. This is essentially done using histograms or plots to see how far off a particular value is from what is considered typical. The best course of action for dealing with outliers is to delete them. The reason is that they can impact your analysis if you leave them in. Here's an example. Assume that you need to calculate the average age of your patient population. If you have an outlier, such as a 1,200-year-old in your analysis, this could sway the calculated mean upwards. By removing this outlier, this would cause the mean to be a much more representative of the typical age. Another step in the data prep is rescaling data. When you find that your data does not fall within a normal distribution, you may have to normalize the data using a rescaling method. When you have numeric data that is positively skewed, you can do what is called a log transformation. Essentially, if you take the natural log of each numeric data value, this will rescale the data into a normal distribution. Another method is to recenter the data by subtracting the mean from each value and dividing by the standard deviation. A third option is to rescale the data in a range from 0 to 1. A fourth option is to rank the data from lowest to highest. Regardless of the rescaling method, the thing to understand is that the purpose of rescaling is to force a normal distribution onto your data. The issue with this is that it will change the inherent meaning of your data because the data is formatted in a different, less familiar scale. Therefore, this method is appropriate only if you need to run an inferential statistical method that requires your data to be normally distributed. The last method we will cover regarding data prep is recoding data. This method is most common when you want to create a categorical data or change the look of an existing categorical data element. Sometimes you may need to convert numeric values into qualitative bins. For instance, if you have data on patient's age, you may want to convert that column into age groups. For instance, you may want to record the data into age groups 0 to 3-year-olds, 4 to 8, 6 to 11, 12 to 15, 16 to 19, and so on. Recoding may also be required when you convert categorical data into binary outcomes. For instance, if you have a column of eye color, you may want to know how many people had blue eyes. Therefore, you can recode the data for those with the blue eye color as a 1 and any other eye color as a 0. This will create a column of just zeros and ones, where 1 indicates blue eyes and 0 indicates non-blue eyes. Another example is to redefine the existing categories. For instance, the data for sex may be coded as 1 for male and 2 for female. But instead of a 1s and 2s, you want to show the text males and females. Therefore, you recode the 1 to male and 2 to female. Final recoding example is to join categories. You may have a column of data for patient satisfaction scores, which included not at all satisfied, not satisfied, neutral, satisfied, and very satisfied. You may want to combine the categories not at all, satisfied, and not satisfied, and recode them as low, while the satisfied and very satisfied are recoded as high. All of these examples are ways in which the data can be recoded to support an analysis. In conclusion, data quality is something that needs to be achieved during data capture, database development, and data analysis. Knowledge about the data elements is essential when preparing data, and the process can be subjective. Finally, sometimes the best solution to avoid using some of the data is to just delete it.